Hello students, welcome to Sri Jayendra's Ring Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 11 of our unit moving charges and magnetism. So let's begin with today's class. This is the class for the moving coil galvanometer. In short, which is even used to have name, it's an MCG. It's a moving coil galvanometer. So now let's begin. First question, what is galvanometer? What do we mean by this? We can say that galvanometer is an electromechanical instrument which is used for the detection. Please have a focus on this word. It is used for the detection of electric currents through electric circuits. So the question is, does galvanometer measures heavy currents? The answer would be no. It cannot. It can only measure small amount of currents, and the primary purpose of galvanometer is the detection of electric current but not the measurement of current. So I hope you have a differentiation in your mind that galvanometer is not used to measure the current. That means galvanometer directly cannot say the current is 2 ampere or current is 3 ampere, or let's say current is 5 milliampere. Galvanometer is there which can say that current is there, yes or no, current is not there. So it can say only yes or no. It can have a decision of yes or no only. It could not tell us that this amount of current is being flowing. Does it clear? Does it? Great. Now how do we measure current and voltage? If we can say that if galvanometer is not going to tell us that 5 ampere current is flowing, then how do we measure the currents and the voltage? So same thing, it's in how do we claim that the current in a circuit is 1.5 ampere, or a voltage drop across a certain resistance is 1.2 volt. So what we are supposed to do is moving coil galvanometer. It's an MCG, exhibits a very useful instrument for this purpose. That means we are going to have certain modifications in the MCG, moving coil galvanometer, and then it will be capable to have an answer that what amount of current is flowing and what amount of voltage is flowing. I hope it is clear. But MCG in its purest form, MCG, moving coil galvanometer, in its purest form is not capable enough to tell us that what amount of current is there or what amount of voltage drop across certain point or across certain resistance. So let's first look how the moving coil galvanometer look alike, on which principle does it work, and how does it work, and then we will switch to the answer that how I can measure the current or how I can measure the voltage. So let's begin. First, we are just looking for the moving coil galvanometer. We can say it's an instrument used to detect and measure a small electric current. So if you can observe this very carefully, this is the construction, or this is about to look like a galvanometer. That north pole and south pole of magnet would be there. Coil has been winded over here, and this is the calibrated scale which from we, that means we as a user, see it. I hope this is clear. This is the north pole, this is the south pole, and everything is clear. I hope. Is it clear? Is it? Now now moving coil galvanometers are used in the cockpit of an aeroplane. Even they are used, MCGs are used in all kinds of different equipments, from aeroplane cockpit to sound level meter in recording studios. Yes. So it has been used, it has very wide applications when we talk about the MCG. So let's discuss that on what principle does MCG work. It works on the principle that a current carrying rectangular loop, when placed in a uniform magnetic field, it experiences a maximum torque, but it does not experience a net force. So it is having only the net torque on it, and the net force is zero. Let's find it out how it has been become its construction. So it consists of n turns of coil PQRS that wound over a non-magnetic metallic frame that generally it is a rectangular or somehow circular in shape, and this coil is suspended from a torsion head edge by means of a phosphorus bronze strip in a magnetic pole by pieces, north pole and south pole. One more thing, a mirror is attached, a mirror M is attached to the phosphorus bronze strip, and the other end of the coil is connected to a hairspring, which in turns is connected to an external terminal. So this is the pointer, you can show this is the pointer which will represent the current, and this is the 2D diagram of the situation. So you can see this is the north pole, this is the south pole, and this is the rectangular coil. I hope you can see this is the rectangular coil, and this has been connected, and this is phosphorus bronze strip. Yes, please, this diagram is useful when we are talking about the subjective examinations. That means your board examination, this can be asked. Yes, that working principle or construction of MCG. So what we are supposed to do is, if you observe this very carefully, we used a concave or cylindrical pieces, we can say it's a pole pieces, ensure that the plane of the coil is always parallel to B. The plane of the coil is always parallel to B, and while plane of the coil is parallel to B, that means cos theta, it's a cos of 0 degree would be equals to 1, and sin theta would be equals to 1, because this is the area vector, and when for area vector it's a theta is equals to 90 degree. So this sin 90 would be equals to 1, and this is the cos 0 degree. Yes, so in this expression, torque could be equals to NIBA cos theta and NIBA sin alpha. This is the symbol of alpha. So the whole arrangement, this complete arrangement is enclosed in a non-magnetic case, because a magnetic case can have its effect too, because it can work, because it is working on the principle of magnetism only. That's why we choose a non-magnetic case, so that it could not have any effect on it, and we are using non-magnetic case, which is provided with leveling screws, and the torsion has is connected to the terminals T1 and T2. Now let's look at the working of this. So when we say it's a when current is passed through the coil, we can say PQRS. The coil is experiencing a torque that is equals to torque equals to NIBA sin alpha. Yes, how this torque will act on it, we have just see this in the previous class, that this torque acting on the current carrying coil. Yes, so based on that, torque is acting, and when torque is acting, we used to arrange the magnetic field, which is a radial one. We used to arrange a radial magnetic field, and the plane of the coil is parallel to the magnetic field, such that this alpha should be 90 degree always, and this torque is the maximum, which is NIBA. I hope this is clear. Every time what we want or what we expect is that torque acting should be a maximum, and that can be provided using this radial magnetic field. Otherwise this is simply not possible to have a torque which is a maximum one. Got it? So the coil rotates and the phosphorus bronze strip gets twisted. As a result, a restoring torque comes into play, trying to restore the coil back to original position. Let us suppose understood that phi is the twist produced in the strip, and C be the restoring torque per unit twist. We say this as a toroidal constant. Yes, so C be the restoring torque per unit twist, when the restoring torque could be written as C into phi. So in the equilibrium we have a two torque. One first, it's a NIBA. This is the torque acting on the coil because current is flowing through it, and now because my strip gets twisted, it is having a restoring torque. This is equals to phi into C, where phi is the angle twist produced in the strip, and C is the toroidal constant. For in equilibrium, for equilibrium, this two would be the equal. It's a NIBA is equals to phi into C, and from this I can have a current which could be calculated. It's a C into phi divided by NBA. I hope this is clear. Is it clear? Is it? So where I can write, it's I is equals to G into phi, where G, I have replaced this G with the C by NBA, and G can be said as, it's a galvanometer constant. C is said to be as a galvanometer constant, and if I understand that this all are the constant, then I can have, it's an I which is directly proportional to the phi. So whatever the deflection is, higher the deflection, higher the current, lower the deflection, lower the current. So at this stage galvanometer has a linear scale and detects the presence or absence of a current. I hope this is clear. It is just the I directly proportional to the phi. So if phi is higher, I is higher, and somewhat like this. So at this point of time, you must understand that our galvanometer is capable enough to to detect that current is flowing or not. That's it. Nothing more than that. Nothing more than that. I hope this is clear. Is it clear? Let's see certain theoretical questions based on the theory we have already discussed. Yes, so first the lamp and scale arrangement is used for measurement of deflection ends. They are used in the suspended coil type MCG, pivoted coil type MCG, tangent galvanometer potentiometer. They are used in the suspended coil type moving coil galvanometer. Is it clear? Next, horseshoe magnet. Horseshoe magnet is cut into these concave pieces or convex pieces, flat pieces, circular pieces. They have been cut into the concave pieces. Why? Why so? Because they can arrange radial magnetic field. They can arrange a radial magnetic field to the coil. So as they can arrange a radial magnetic field, they have been cut into the concave pieces. Why radial magnetic field is required? Because the situation is torque equals to NIAB sine theta. What I want that theta should be always 90. Why do I want? Because it is the only case when torque would be maximum. That could be given as NIAB. Yes, we must be very clear. We must be very clear with this concept. Yes, then only then we understood the working, and then only then we would be capable enough to do the numericals. Yes, let's look at the next question. The function of soft iron core cylinders. So first it's the mag field radial as well as increase the magnetic flux. Yes, so their work is both 1 and 2. Yes, they are the core cylinder, soft iron core cylinders are used to make a radial magnetic field, as well as once the fields are radial, magnetic flux will be automatically increased because it will create a phi is equals to B dot A. Yes, it's a magnetic flux dot product with the area vector. Next, if the current is parallel to the magnetic field, then the force acting on it, yes, force acting on it is 0. Why? It's an F is equals to BIL sine theta, and in this case theta is equals to 0 degree, and if theta is equals to 0 degree, this force would be equals to 0. So this is F is equals to BIL sine theta. Theta is 0, and as theta is 0, force is 0. Is it clear? Is it? Are you sure? Yes. Are you sure? Now we would be having an answer that how we can convert galvanometer to ammeter. Let's have a look. It's a conversion of galvanometer to ammeter. So first thing, what is ammeter? What is ammeter? As you have studied this in class 10, probably in class 9 too, in certain syllabuses. So ammeter, it is a device. It is a device which is used to measure current. So what emitter is? Emitter is a device which is going to be used to measure a current. That's why we are going to use the emitter. Now, now what we are supposed to do is we are going to convert this galvanometer to emitter. How do we convert it? Let's have a look. It's conversion of galvanometer to emitter. So galvanometer can be converted to an ammeter by simply connecting it with a low resistance called a shunt in parallel to the galvanometer. When and when they are using the word shunt, they want it to connect in parallel. Even if you remember that we have used this word shunt in the third unit as well when we were discussing the certain part of current electricity. One more time here, that when and when we used to have a word shunt, that means we are talking about the parallel. So what we are supposed to do is that, let's suppose this is the situation, and let's say this is galvanometer, this is the internal resistance of galvanometer, and certain current is flowing through this. Now what I want, if I want that, I want to bypass this path. Why? Because a certain heavier current is flowing through it, and my galvanometer is very sensitive device, that it cannot have, or it cannot allow to pass a larger amount of current. If by mistake a larger amount of current has been passed through galvanometer, it will burn out your galvanometer, so it will destroy it. I hope you understand the meaning of it. So what we are supposed to do is that, this is again the galvanometer resistance and this is the galvanometer. What we are supposed to do is that we are going to use to connect one of the resistance over here. This is RS, and we ensure that this shunt resistance is much lesser as compared to the galvanometer resistance. So you understand that this point, let's say this AB and this CD, these two are connected in parallel with each other. And when these two are connected in parallel with each other, and if this resistance is lower, it is much lesser. In fact, when this resistance is much lower, much lesser, then larger amount of current, let's suppose if I understand I1 and this is I2, then I must understand that I1 would be much greater than I2. Why? Because current always prefers a path which is having lower resistance. This is the basic concept. I hope this is clear. So we are doing the same thing. So let's have a look at the mathematical part of that. So let G is equals to Rg. It's a galvanometer resistance. It is the resistance of the galvanometer. And S, it is the Rs. That would be the shunt resistance. So capital R would be the effective resistance. Then what I am supposed to have is, this is the total current I, and the total current I could be divided into two parts. One is the Ig, another is the shunt current, and the shunt current can be even represented as I minus of Ig. So Ig is the current that has been passed through this, and I minus Ig, that is the current that has been passed through this. So let's suppose understood that R would be the effective resistance, and that R could be represented as, that is the Rg into Rs divided by Rg plus Rs. And this V, the voltage across this, it is equals to IgRg, or we can say ISRs, and that would be equals to I into R. I hope this is clear. Is it clear? Great. So we can say so that IgRg is equals to ISRs, and this IgRg would be equals to I minus Ig into Rs. If I solve this, I can have this. It's an Ig is equals to I into Rs upon Rg plus Rs. It's G would be a subscript. It's a resistance of galvanometer, plus Rs. It's a shunt resistance. Similarly, I can have that the shunt current would be this, and shunt resistance could be calculated like this. I hope this is clear. Is it clear? Is it? Yes. Rs could be calculated as Rg upon n minus 1, where n is the I divided by Ig. and this can be said as the range of the emitter. So we understood that as RG and RS, its a situation is something like this. This is RG, this is RS, and the emitter resistance, that means the total resistance, would be equals to RG into RS upon RG plus RS. Yes. So when two resistors are connected in parallel, when two resistors are connected in parallel, the effective resistance would be lesser than even the lesser resistance. Yes. So emitter will have a very low resistance, and that's why only it is going to measure the current. One very good thing, very conceptual thing, ideal emitters have zero resistance. It is always having no resistance, but we are talking about the ideal. While talking about the practical amperes, practical emitters will have very less resistance, that we have already discussed over here. Now let's discuss certain conceptual part, that why, as the parallel resistance is smaller than the galvanometer resistance, why do we connect a resistance which is a smaller one as compared to the galvanometer resistance? Why? So let's have an answer of this. The current or total resistance of circuit should not change due to the presence of the emitter. Therefore, emitter should have very low resistance. And if I want that emitter should have very low resistance, then parallel resistance should be much smaller than the galvanometer, because more current flows through the shunt, and thus if more current or higher amount of current has been flown through this, my galvanometer can be saved, can be protected from high currents. Yes, this is what we have discussed at the very beginning. I hope this is clear. Is it clear? Is it? Now let's discuss the very important part of the galvanometer. It's current sensitivity. The current sensitivity can be defined as the deflection per unit current. So we have this thing, it's an NIAB, that is equals to phi into C. So we are defining it's a phi by A, which could be N into B into A divided by C, which is radian per ampere. It's an ampere. How do I increase it? Look at this. Practically, this is phi by I is equals to N B A by C. So only one of the approach can increase only one of the approach can increase the n, because this all factors are there which is not possible to change it over the time, but n, it is just the number of turns of the coil that can be changed. And if I increase the n, it will increase my current sensitivity. I hope this is clear. Is it clear? Are you sure? Great. So now let's look at certain MCQs based on theoretical session. Let's have a look. First, to convert a moving coil galvanometer into an ammeter, I need to convert galvanometer to ammeter. What should I do? I want a lower resistance in parallel. Yes, so this all are the incorrect option. Yes, what I want, I need to connect the resistance in shunt. While I say shunt, I mean I need to connect it into the parallel. Now, let's have a look. Next question. If the galvanometer is connected in series with the circuit, then the resistance of circuit, what will happen? If the galvanometer is connected in series, we are keeping the resistance of galvanometer. We are keeping the resistance of galvanometer very less, that it cannot affect total resistance, that if cannot affect the total resistance of the circuit. So circuit or circuit's resistance will remain same. Does it clear? So I will arrange the situations such as the resistance of the circuit should remain the same and it should not affect, so connection of galvanometer should not have a effect over it. So we arrange such things so that resistance of the circuit will remain the same. Next question. A shunt is, what is shunt? It's a low resistance while connected in parallel. It's a low resistance connected in parallel to the galvanometer, so that that galvanometer can work for us using an as an ammeter. Does it clear? Does it does it clear? Great. So now what we are supposed to do is we will just understood that how galvanometer can be converted to voltmeter, and then we will see the numericals of both. So let's first look at the conversion of galvanometer to voltmeter, that how galvanometer can be converted to voltmeter. Let's have a look. So this is conversion of galvanometer to a voltmeter. How will we convert? Let's have a look. We can say that a galvanometer can be converted to a voltmeter by connecting a higher resistance in series, and we can say that a voltmeter is used to measure the potential difference between any two points in a circuit. Yes, why voltmeter is there? We can have, it's a voltmeter is used to measure the potential difference between any two points in a circuit, and voltmeter must always be connected. Must be connected in parallel in the circuit. So what we are supposed to do is we are going to connect a certain resistance in series with the galvanometer. This is the Ig, that is the maximum current that can flow through the galvanometer. It's an Ig, and this is the resistance of the galvanometer, and the certain resistance has been connected, certain external resistance, I must say this, has been connected in a series with the galvanometer. So now this complete construction can be called as the voltmeter, which is used to measure the voltage, or I can say potential difference of across a resistance or across a two terminals. The value of the series resistance R to be connected to convert galvanometer into a voltmeter is R is equals to small r plus Rg. Let's suppose understood that Rg is the resistance of the galvanometer and R be the parallel resistance, and capital R would be the effective resistance. Yes. So the potential difference between A and B, that is equals to V is equals to Ig into bracket R plus Rg, and the total potential difference could be written as it's an Ig into R plus IgRg. From this I could have this R, which is equals to V by Ig minus of Rg, and from this, if I solve this, that could be written as Rg into bracket V upon IgRg minus of 1. If I define N as the range of the voltmeter, that could be written as V upon IgRg. So this can work as a voltmeter of a range from 0 to V volts, and always remember this thing, that voltmeter is having a higher resistance. When I talk about the ideal voltmeter, we can say that an ideal voltmeter has infinite resistance, and conductance, when I say resistance is infinite, I must understand that conductance, which can be represented as Z, would be a 0. So conductance of an ideal voltmeter is 0, and we are ensuring that higher resistance of the voltmeter does not affect the potential difference measured by it. which draws a very small current. I hope this is clear. And we can say that potentiometer, have you remembered this? Why do we use it? Potentiometer, why do we use it? Yes, to potentiometer has been used in current electricity, which is used to measure, which is used to measure the potential drop, potential drop between 2 points, or we ideally say it as an EMF because current has not been drawn. So potentiometer, even potentiometer is an ideal voltmeter. Is it clear up till now? Is it clear? Any doubts, any concern over this? Is there anything? Is there anything? No? Great. So let's look at certain logical questions behind this. First, why is the series resistance that is greater than the galvanometer resistance? Why do we choose this? Because voltmeter has to draw a negligible amount of current from the main current, therefore it should have a higher resistance. So if resistance is higher, look at this, this is the situation, this is Rg and this is the R external that has been connected to make this, to make this a voltmeter. So when I say this, that if I amount of current is flowing, if this resistance is smaller, let us suppose that if I choose this resistance as a smaller, then higher amount of current can flow through this, and higher amount of current pass through galvanometer can damage my galvanometer. So if this is not to happen, I choose this R external which is higher, so that this total resistance, the total resistance of this would be much higher, which does not allow higher amount of current to flow through this, and which can protect my galvanometer. I hope this is clear. Yes. So the series resistance must be greater than the galvanometer resistance. Is it clear? Is it? Great. Now, voltage sensitivity. As a current sensitivity, we have voltage sensitivity too. It can be defined as the deflection produced for a unit voltage applied across the two terminals of a galvanometer, and that could be written as phi by V. Now V can be written as I into R, so this is phi by IR, and phi by IR can be replaced as NBA by CR, radians per volt. Now the question is, how, or shall I ask that, can we increase n, that is number of turns, that you understand, can we increase n to increase voltage sensitivity? Think over it and let me know. Can we do this? Can we increase n such as voltage sensitivity can be changed, or voltage sensitivity can increase? Can we do this? Can we? Look at the formula very carefully. Phi by V, this is equals to NBA divided by C into R. Look at this very carefully and let me know. If I am going to increase the n, then automatically R will increase, because what do you understand by increasing n? Because we are going to add up certain number of turns of wire only, na? Yes or no? When we increase number of turns, we are going to add up certain number of turns, and that turn, that wire will be always with resistance. So n, if n is increased, we can say if n increases, R increases. So by increasing n, phi by V cannot be changed. Please keep this in mind. Cannot be changed. I hope this is clear. Is it clear? Is it clear? Let's have certain logical questions in the form of multiple choice questions. Let's have a look. It says that the resistance of galvanometer should be increased. The resistance of galvanometer should be increased so so that a very small current flows through it or a large current flows through it, no current flows through it, or none of this. Yes, so that very small current can flow through it, because if larger amount of current has been flown through the galvanometer, it will damage the galvanometer. So what I want that smaller amount of current can pass, and that can be only achievable if higher amount of resistance has been connected with the galvanometer in this series. I hope this is clear. Next, an ideal voltmeter has, what does it? An ideal voltmeter has infinite resistance. An ideal emitter, yes, it is having a zero resistance. An ideal voltmeter, it should be having an infinite resistance. Let's look at this question. A galvanometer modified to measure the potential difference is called as the, this is what we call as an voltmeter. It is a device used to measure potential difference. Does it clear? Does it does it clear? Are you sure? Any doubts up till now? Is there anything? No? Let's check that. The difference between voltmeter and ammeter. So let's have a look at this. So what is the difference between ammeter and galvanometer? Ammeter is there, which is used to calibrate. It is calibrated in amperes or in submultiples, while galvanometer has only divisions without having any calibration. Ammeter is used to measure large currents, while galvanometer is used to measure small currents. In ammeter, the zeroth division is at one of the end of the scale, while in the galvanometer, the zeroth division in this is at the middle of the scale. In ammeter, the effective resistance of ammeter is very low, and even this is same that resistance of galvanometer is also very low. Let's check the similarity and differences between the ammeter and voltmeter. Ammeter is to be connected in series always. Voltmeter is to be connected in parallel. Resistance of ammeter is comparatively lower, and resistance of voltmeter is comparatively higher. Use of the ammeter, it is used to find the amount of current flowing in the circuit, while voltmeter, it is used to find the potential difference. Please mind well, it is used to measure the potential difference in the circuit. While using in the circuit must be disconnected in order to attach the ammeter. While voltmeter circuit does not need to be disconnected, and that can be applied directly. Accuracy considered as less accurate. If I compare it with the ammeter, this is considered as a more accurate as compared to the ammeter. I hope this is clear. So this is just the comparison. This is just the comparison between the ammeter and voltmeter. So now let's work for the questions based on ammeter and voltmeter. So let's begin with the questions. Let's begin. The question says that a galvanometer has a resistance of, 30 ohm and a current of 2 milliampere is needed to give full scale deflection. What is the resistance needed to convert this galvanometer this galvanometer into, first I need to convert this. I need to convert this into an ammeter, into an ammeter of of zero point 0.3 ampere range. And second 2 into a voltmeter of zero point 0.2 volt range. So go through the data once and take your decision that what is to be done and how this is to be done. So the data says that a galvanometer is there, and the galvanometer has a resistance of 30 ohm, this is Rg, and a current of 2 milliampere is needed to give full scale deflection. Now the one new term, it's a full scale deflection. What does it mean? When they say full scale deflection, that means that means it is the maximum current, it is the maximum current that can pass through galvanometer safely. Full scale deflection, it is the maximum current that can pass through galvanometer safely. Yes, so when they say it's a full scale deflection, that means this is the maximum amount of current that can be passed through the galvanometer. We cannot have current that is more than this, the current that is more than this that can pass it. Yes, so the question is, what is the resistance needed to convert this galvanometer into? First we need to convert it into an ammeter of zero point 0.3 ampere range, and we need to convert this into a voltmeter having zero point 0.2 volt of range. I hope this is clear. So let's first start doing conversion of conversion of galvanometer, conversion of galvanometer to ammeter. So let's convert the galvanometer to ammeter. How can I convert this? So what we are having is that when I need to convert this to ammeter, I just connect a shunt resistance. I just connect a shunt resistance, and when I say shunt, it is by default clear that it is to be connected in parallel. So this is what should be the range readed? Yes, it's a zero point 0.3 ampere. So this should be the 0.3 ampere, a certain current that can pass through this, and that certain would be the 2 milliampere, as it say it's a full scale deflection. So the remaining amount of current can pass through this. From here it's a 0.3 it's a zero point 0.3 minus of 2 into 10 to the power minus 3 ampere. This current can be passed through this, and this is the shunt resistance. I hope this is clear. Now what I needed the value of the RS. I needed the value of the RS. So how could I do this? So for doing this, I understood that if you don't remember any formula, then even it could be done. Let's suppose this is A, this is B, this is C, this is D. This looks in the parallel. So what I can do is, it's an IGRG that should be is equals to I minus IG multiplied by shunt resistance. IG, it's a 2 into 10 to the power minus 3 into Rg, resistance of galvanometer, that is resistance of galvanometer. What is it? Yes, it's a 30 ohm. That should be is equals to I minus Ij. It's a 0.3 minus 2 into 10 to the power minus 3 multiplied by shunt resistance Rs. I hope this is clear. So if I solve this, look at this. Rs could be calculated as this is 2 into 10 to the power minus of 3 into 30 divide by, look at this, this is 0.3, this is 2 divide by 1000. So I hope you understand that this factor does not have any significant effect on this 0.3. So for an approximate calculation, we can have this as a 0.3, and when we do this with this, it would be 0.2 ohm. So what I need to do is I need to connect a resistance of zero point 0.2 ohm in parallel to the galvanometer. That will convert my galvanometer to the ammeter. Is it clear? Is it clear? One more thing, that you can understood that this RG, this was the resistance having 30 ohm, and this resistance is only a zero point 0.2 ohm. Yes. So as this resistance is much lower, so most of the current, it's approximately complete current, because we have taken considered as in zero point 0.3, or we can understood that very little current has been passed through this, and the most of the current has been passed through this. I hope this is clear. Is it clear? Is it? Are you sure? So so this is the resistance that is needed to be connected. This is the resistance that is needed to be connected in parallel with the galvanometer, so that this can behave as an ammeter. I hope this is clear. If someone asks me, that what would be the resistance of ammeter, then resistance of ammeter could be written as, this is Rg multiplied by Rs divided by Rg plus Rs. So this is the resistance of a meter. If you understand that this value will be less than the zero point 0.2 ohm. I hope you understand this, because these two are connected in parallel, and in the parallel combination, always the equivalent resistance is lesser than the element having the least value. I hope this is clear. So even this would be the less than zero point 0.2 ohm, and that's why we can say that when we are connected ammeter with a circuit, it does not the resistance of an ammeter does not have any significant effect on the circuit's resistance. So everything is clear. Does it clear? Does it? Great. Now let's move to the second part, that is conversion of of galvanometer to voltmeter. We are now converting a galvanometer to voltmeter. So let's begin. What 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 range is required? So I need to convert this to a zero point 0.2 volt. I required a range of zero point 0.2 volt. So what we are supposed to do is, we are just connecting this Rg, that is the galvanometer resistance, in a series, and this is the R external, that is Rx. I am looking for it. The current, this is the 2 milliampere. It's Ig max, that is the maximum current that can pass through this, and this Rg is having a value of 30 ohm. So what we can do is, let's suppose give them a name, it's an A, this as a B. So VAB, that should be is equals to I multiplied by galvanometer resistance plus Rx. When I write VAB, that is equals to zero point 0.2 volt is needed. So this is 2 by 10. That should be is equals to current. This current would be equals to 2 into 10 to the power minus of 3. And this Rg, it's a 30 plus Rx. I hope this is clear. So if I solve this, it would be, this 2 and 2 has gone. This 2 and 2 has gone, and this would be, this is the, so 1 divided by 10 into 1 divided by 10 to the power 3. I hope this is clear. Is it? Does it? So this zero point 0.2 volt is required, a range of 0 point 0.2 volt is required, and this is equals to 2 into 10 to the power minus of 3 into Rg, galvanometer resistance is, it is of 30 plus R. So this is equals to 1 by 10 is there. Yes. And this is 1 by 10 to the power 3. This is equals to 30 plus Rx. So you can solve this and having a value of Rx. I hope this is clear. Is it clear? Is it any confusion over this? Is there anything? Is there anything? No? Great. So this many ohms are required to convert this many ohm is required to convert this galvanometer into voltmeter. Is it clear? Is it clear? So one more question, one more question for practice. Let's have a look. That it says that the scale of galvanometer, it says that the scale of galvanometer is divided into 150 equal divisions, and galvanometer has current sensitivity. Galvanometer has current sensitivity of of 10 divisions per milliampere. It is having a current sensitivity of 10 division per milliampere. I hope this is clear. Is it clear? Yes. And 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 the voltage sensitivity voltage sensitivity of of 2 divisions per millivolt. How can we convert this galvanometer? How can we convert this galvanometer to first ammeter into an ammeter of 6 ampere per division, and second voltmeter voltmeter of of 1 volt per division. How could I convert? So what is to be done? What they say is, first look at the data, look at the data carefully, take your time of 30 seconds and look at the data. So have you done it? Have you? Yes. So what does it says? The data has been given in certain different method. They says that total 150 equal divisions are there, and in this divisions it is galvanometer is having a current sensitivity of 10 divisions per milliampere and voltage sensitivity of 2 division per millivolt, 2 division per millivolt. Yes. So how can we convert this, how can we convert this galvanometer to ammeter in a range of 6 ampere per division and in a range of voltmeter of 1 volt per division? So how could I convert it? So first you need to understood that what is the full scale voltage, what is the full scale voltage, that is the what is the total voltage that can be measured from this. So full scale voltage can be calculated as number of divisions divide by voltage sensitivity. So number of divisions are 150 and their voltage sensitivity, it's a 2 divisions per millivolt. So if I convert this, it's a 75 volt. Yes, millivolt has been converted to. And what is full scale current to it? It's a full scale current that can be calculated as full scale current a same way, number of divisions divide by current sensitivity. So number of division divide by current sensitivity. So if I solve this, it is the 150 divisions are there, and current sensitivity, it's a 10 divisions per milliampere. So this is 15 milliampere. So this much amount of maximum current can pass through this. Using this, I can have a galvanometer resistance, that is the V by I. The V is the 75 volt, and I is the 15. I is the 15. So this could be it's a 5 ohm. I hope this is clear. Is it is it clear? So now how could I calculate the conversion of ammeter and conversion of voltmeter? I'm having an everything. So let's do it using the formulas that we have derived previously. Yes, we have done one of the numerical according to the approach. Now one of the numerical based on the formulas. So first, convert a galvanometer to ammeter. So when I convert galvanometer to ammeter, this could be written as S is equals to, that is the shunt required, it's a Ig into G divide by it's a I minus of Ig. So if I put up the value, the Ig is 15 into 10 to the power minus of 3 multiplied by galvanometer resistance, this is 5, divide by I, it's a 150 into 6 minus of 15 into 10 to the power minus of 3, that could be given as 8.3 into 10 to the power minus of 5 first. And the second one, it's a galvanometer to voltmeter. Let's convert galvanometer to voltmeter. So I need to connect this into a series one, and when I connect this into a series, I can have the relation, it is R is equals to V by Ig minus resistance of galvanometer. Yes, so that could be given as it's a 150 divided by Ig would be equals to 15 into 10 to the power minus of 3 minus of Rj, this is equals to 5. If I solve this, it would be 995 ohm. So this resistance needed to be connected in series, and this resistance is needed to be connected in parallel. I hope this is clear. Even this was your answer. Is it is it clear? Any doubts up till now? Is there anything? No? So let's just wind up this session over here. This is all about the MCG. It's a moving coil galvanometer, as well as we also know that how can I convert from galvanometer to voltmeter or galvanometer to ammeter. So please have a practice of this kind of questions, as well as please go through the all the required theory sessions that we have discussed, all the required theory data that we require, that why radial field is required, and why horseshoe magnet has been kept, and if we have not kept the radial magnetic field, what will happen, and every that stuff. Yes, please go through it once, because now NTA has started conducting examinations, and NTA mainly focus on the theoretical sessions as well. So up till now, there are very little questions has been asked from the theoretical point of view, but as NTA has started taking examinations, they are asking some or other information regarding things every year. So please do it. This is very required for us. Thank you, have a good day, take care, bye bye.